Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is one of a series on circular motion, and it starts with the basic concept of angular speed. In order to deal with angular speed, it's important to have the idea of radian measure. Now, radian measure is no more than a change of scale when measuring angles. First, let's take that we have an angle defined by two lines coming from a point, and on that same point we base a circle. So we've basically got a picture of a sector within a circle, and the sector carries the angle. So associated with that, then we automatically have a radius and an arc length, denoted in this case by S. So S is the arc length for that sector. Now, the angle defined in radians is the ratio of the arc length S to R. It's basically just that distance, the arc length, divided by the radius. So that's expressed in that equation, and it has the immediate consequence that if we measure an angle in radians, then the arc length on the circle is simply the radius times the angle. Now that raises an immediate question. If we have an angle, we use a circle of radius r, what happens with the same angle if we use a scaled up situation where the radius has become kr, and so consequently the arc length has become ks? All circles are similar, so corresponding distances will expand by the same ratio. So we have the same angle there, but in two different circles. Well, since S over R gives the angle, and in the first case that's just simply S over R, and in the second case Ks over R, where the Ks will cancel, we will always get the same answer. So it doesn't matter what the size of the circle is. We can put the same angle on those two diagrams, and we'll end up with the same value for theta whether we use S over R or Ks over Kr. So an angle defined in this way is independent of the size of the circle. Well, okay, then we're going to use radian measure. Why do we do that? Well, that won't become apparent in this particular video, but the answer is bound up with how we apply calculus to trigonometry, which is further down the line, but that is essentially the reason. So our definition is that the angle is the arc length over the radius, or alternatively we can put it that the arc length is the radius times the angle. So what then do we mean by 1 radian? Well, 1 radian would be when this value works out to be a 1. So this distance is 1 when this length is 1, or alternatively, if this length is r, this distance will be r. In either case, the ratio of the arc length to the radius will be 1. So 1 radian is defined as the angle subtended at the centre of a circle by an arc of length equal to the radius. So how many radians do you get in a full turn? Well, a moment's thought should tell you that the answer to that's easy, because if you took a full turn, so the angle you're talking about is the full turn, the arc length is right the way around, the arc length will be 2 pi r in terms of the r, so when you do the arc length over the radius you'll get 2 pi. So a full turn is 2 pi radians. So there are 2 pi radians in one full turn. Sometimes radian is denoted by C there. That should be read as 2 pi radians, or 2 pi in circular measure as it's alternatively called. So we've got the useful consequences that 2 pi C, or 2 pi radians, is 360 degrees, and pi is 180, and correspondingly 90 degrees will be pi by 2. And you can go on calculating those simple correspondences. Pi by 4 is 45 and pi by 6 is 30 degrees. Well, now let's look at circular motion. We've got something moving in a circle. Now the immediate thing that we require is a way of describing its speed. Now velocity is constantly changing. If the particle moving in a circle is at B, then its velocity will be directed along the tangent, which is roughly that way. But if you take it at A, then its direction has changed. So it's no good talking about a constant velocity in a circle. That would be nonsense, because the direction's always changing. You can have a constant speed, and that will correspond to a constant angular speed. So instead of thinking of the distance covered along the circumference, we think in terms of the angle that's opened up as the particle moves round. So in this case, we've got an angle of 1.5 radians is covered in 1 second, so its angular speed will be 1.5 radians per second. Now that's the normal way an angular speed is expressed, in terms of radians per second, and there will be a consequence of that, as we'll see in a moment. If we use degrees, it is far more complex, but in terms of radians we can easily express the speed at B in terms of the angular speed, as we shall see in a moment. So the standard unit for angular speed is radians per second. Now, an alternative notation, hey presto, look, that omega, which is the standard letter that's used for angular speed, is turned into theta dot. Why that? Well, because if you think in terms of the angle that's developed over time, there's a rate of change of angle, and that d theta by dt is an alternative way of writing the omega. So if you like, there's an omega written there that's not included from the previous slide, and theta dot is simply a shorthand for d theta by dt. This calculus notation on the one level is very informative, but on the other hand it's very clumsy, so often it's replaced by theta dot in mechanics considerations. Well, converting angular speeds between units. What's the angular speed in radians per second of the following? You take an object that makes 3 revolutions of a circle in 1 second. Well, if it does 3 revolutions, it's covered 3 times 2 pi radians, and that's in 1 second. So that's equal to a speed of 6 pi radians per second. What about a turntable spinning at 45 revolutions per minute? Well, 45 revolutions means that you've covered 45 times 2 pi radians in a minute, and an angular speed will be the angle covered divided by the time, which is 60 seconds to use standard units. So we'll end up with 90 over 60, which is 1.5 pi radians per second. So there we are, those two calculations carried out. Now let's look at the relationship between angular speed and linear speed. This is where radians really come into their own. First of all, think about how linear speed is related to the situation we see here. The distance from the starting point, if we imagine that it started when I put that dot, the distance is the arc length, and so the velocity, not the velocity, the speed. It's easy to make a slip like that with the vocabulary. You have to say speed in this context. The speed is the rate at which that s increases, but s in turn is r times theta, so we'll soon see that we get an easy relationship between the two. So taking the rate of change of s, ds by dt is d by dt of r theta. And since r is a constant multiple, then we get r times d theta by dt, or to use the old language, the old notation, r omega. Now that relationship v equals r omega is fundamental to circular motion, and it goes back to the fact that you're using radian measure. It wouldn't be true if you used degrees, and it's at this point that the point of radian measure becomes quite clear in this context. So v is r omega is the fundamental relationship between the speed of a particle in the circular path and the angular speed. So you notice I've put that fundamental relationship up in the top corner because that's what we shall refer to. So here we've got a typical context. We want the speed of an object that's travelling in a circular path, and the circular path has got radius 20 centimetres. Now we should immediately have an instinct to recognise that 20 centimetres is not the right units, so we'll say in this context that r is equal to 0.2 working in metres, and the angular speed is 8 radians per second, so 8 is omega is equal to 8, so our standard units, in a sense, without saying so, we've extended our idea of standard units to say that when we're talking about circles we use radians and hence radians per second, and so the relationship that we have in the top right hand corner of the slide says that we need to work out 8 times 0.2, which is 1.6, and that has to be meters per second. So there we have the calculation and the answer in context using the units. Well, that brings this particular video presentation to an end. The next one in the same series on circular motion focuses on acceleration. I hope to be with you later to explore that.